Okay, today we're discussing the definite integral, and this definite integral is described as a collection of summed columns. In the past, you had seen earlier in Chapter 5 summation and approximating the area under curves using rectangles. And finally, the most accurate method was using rectangles centered under the midpoint by measuring from the midpoint of these rectangles. And so you have a curve, let's say, with 4 rectangles under it, and this region goes from 0 to 3. You would have 4 midpoints, such as, for example, at 3/8, 9/8, 15/8, and 21/8. These are between 0 and 3, 4 points evenly spaced that are rectangles that we'd be measuring from. And this would be an approximation of the area under the curve of function f. And so what you get now that you didn't get earlier was the formula for these midpoint rectangles. And this is a general formula that you can apply to any of them. In this case, I showed 4 terms for 4 rectangles, n equals 4. The first one is a little bit trivial here because it's multiplied by 0. So this entire region right here is actually 0. But then later we actually have these terms that are summed 1 times this ratio, 2 times this ratio, 3 times this ratio, and what you end up with are these measurement points for your function at these midpoints of these rectangles. And so this would give you the input to the functions, such as if your upper is 3, as in right here, and your lower is 0, and n is equal to 4, you would get that for 0, 1, 2, and finally n equals 3, you would get these ratios, those values, from these 4 equations. And of course, if you wanted a fifth term, you would just set n equals 5, and then proceed onwards for 0, 1, 2, 3, and 4. Basically, the last value would be n minus 1. So in a sense, n minus 1, n minus 2, n minus 3, n minus 4. Those are the values and what you would put in for the red numbers. And you can see doing this is pretty tedious. You can be a little bit more abstract about this and just say the width of the rectangle is the width of this partition size, and that we want there to be enough of these rectangles so that this width is smaller than some number delta. So we give a minimum size of in a sense it's like a kind of error space that we're allowing ourselves to have. And so our rectangles must be sized so that they're smaller than this delta, and if you make delta small enough, you will end up with more and more of these rectangles of this given partition width. And so there is actually an exact integral value known as I, and you haven't really seen too much of how you figure out the value of I, but as you have more and more of these rectangles of these partition widths, you'll get to more closely approximate the value of I. And the difference between the sum of all these rectangles and I is an error. and that's represented by this epsilon. It looks like a little e, which I think is why they chose that symbol to represent error. And so basically, an integral is the limit of a Riemann sum. The integral being the area under the curve, it would be an infinite summation of very, very skinny rectangles under the curve. The sum of these rectangles is called the Riemann sum. So you have a width of delta x of k and a height of the function of c of k, where c of k is the midpoint of that rectangle, and derived from those equations which I've shown on the previous slides, a few slides back. And so what you actually see here is this is the height of the rectangle, and the width I'm going to box in blue. That's the height times the width of these summed rectangles. This is their summation, and that's and so we have an infinite number of heights times width that we're adding up with a summation, and the sum of all those from the first one to the nth one, you subtract away the exact value I, and you'd hopefully get a very small number. This number e becomes very, very small as this number n becomes very, very large. So the incentive is create a large number for n, and the expense of that is computational time. It takes time to calculate each one of these rectangles' area, but the more you do it, the reward is a more accurate integral. You can actually have a computer calculate these multiplications for you, and you'll get a very, very accurate value for the area under the curve. There are many types of functions where actually this is the most straightforward method of finding the integral. And so here is an example. The limit as the partition size becomes very, very small, as we go from k equals 1 to n. And this is of this function. This function is the height. I'm going to circle in blue here the height part, and delta x I'm going to do in orange is the width of our rectangles. And we have a starting point of 2 that goes on till 3. And so we have each is a multiplication. Each rectangle, it's the width times height. And so as our partition length becomes very small towards 0, the number of rectangles will increase upwards towards infinity. And so since our p goes from 2 to 3, well, it seems to us like a very short interval. That's going to be where our c of k value is going to start and end. It's going to start, for example, like 2.000, 2.001, 2.002, and after 1,000 or so of these, you would end up stopping at 3.000. That's for the case in which the partition width is 0.001. That actually would be a very accurate summation for measuring the area under the curve. You'd have a few digits of precision there, about 3 digits of precision. And so the key is to recognize that this is actually the integral of 1 over 2 plus 2x. Notice that if you change a c of k into an x, you would have your f of x. That's your the elevation of your curve. And so there's a little bit of translation can be made here, that the partition from 2 to 3 is actually the range of the definite integral that we see. There's our 3 as our upper limit, and the lower limit is 2. The lower limit is where it starts. The upper limit is where we end. The summation of these rectangles, their height times width, can actually be directly translated by turning the c of k into an x, and this delta x, the very, very small, the width of this rectangle, can be turned into this notation dx. And this dx is a notation that is attached to the integral symbol. So whenever you're drawing this integral symbol, this curve shape, you also need to draw one of these, a dx or dy, dt, whatever. There must be a letter d here, and there must be a second letter following it. And this x is important because it tells us, okay, to which variable are we doing this integral with respect to? You can only do an integral with one variable at a time. So you have to tell which one it is, because what if there was like a y in here? Then you wouldn't know which one, and because it would be changing in 2 directions. So it's important to describe the x or whichever variable it is that you're taking the derivative, the integral with respect to. And so this is the formal notation of the definite integral. The definite integral is different from an indefinite integral only in these boundaries. The indefinite integral is missing these, and it is a template for what the integral function looks like. As soon as you have these limits on here, your definite integral would be the area under the curve, but only for that specific region. It's a more specific, limited case of the area under the curve. To find a total area under the curve, for example, a could be a negative very, very large number, such as something approaching infinity, and b could be a very large number, something is approaching a positive infinity. And you would have the entire area under a curve, which could also, by all means, approach infinity. They don't always, but a lot of times they do. And so you have your function, and then you describe the variable with which you are integrating. That's important because you don't always just have one variable in your function. Your function f may actually depend on multiple variables. The variable of integration, the dx, that's part of the symbol. You don't draw the symbol for integral without drawing the variable of integration, like your dx, your dy, or your dt. And you need to do this operation with respect to a certain variable, like x or y or t. And a continuous function across this interval will have a definite integral. If this curve is continuous and was without a fracture in it, without a break, where it's undefined, if there's no place where it does a instantaneous turn, this function will have a definite integral, and it will exist. So properties of definite integrals, these properties are important. Look at these in your book. The these can be used to make very difficult problems soluble. One of these, it's important, is the order of integration. From B to A, you're taking it in the other direction. You're going from its opposite direction from A to B. So when you take these from a different direction, that you're looking at from a different perspective that's in an opposite direction. That means that you will have a negative sign. You'll get a negative value if you take it from the different direction. So if you're standing at A and looking over at B, it's going to be backwards from standing at B and looking back to A. If your rectangle has 0 width, it's going to have 0 area. So taking an integral from A to A is sort of pointless. There'd be no area underneath the curve from, let's say, 3 to 3. There's 0 difference between the starting and the ending. There's 0 area under that curve. Any constants that happen to be inside the integral can come outside. If you have an integral of, let's say, 3x squared, the 3 can come outside. The 3 does not make any difference over the shape of the curve. It's just a multiplier. The integral is going to be a multiple of this multiplier. The same is true if k happens to be a negative number. Negative signs can come outside. You can simplify an integral perhaps by taking the negative out, or sometimes you can simplify it by introducing 2 negatives. That really, a negative of a negative is a positive. It wouldn't change the sign, but sometimes you might want to put a negative on the outside, so you can also put one on the inside. That would be useful in a case where you want to get a negative sign to cancel out. The sum and difference, if you have an addition between of functions that can be separated out with an addition or subtraction, you can do those as separate integrals. That's such as one integral plus another integral. In the case of, let's say, 3x plus 1, 3x plus 1 can be done as 2 integrals. They can be done separately. I shouldn't forget to write dx there to make these true and complete integrals. And a short proof of why this is that I can do by demonstration is look at a curve. If you have a line, let's say 3x, that goes up at this angle, it has a certain slope and has an area under the curve. If you have another one, you're just adding this amount to it that's just that much more. It doesn't change the shape of the curve that already was. It's still a slope of 3. It just has a little bit more area under the curve. And that area under the curve is due to this integral. But it does not, this amount does not change the integral on this side here. They can be dealt with independently. And so you raise a line of a slope up one block. You're increasing that by that much of 1 times the width of your integral. Basically multiplying. Basically adding into it the area of a trapezoid. And so we have the sum and difference is basically, I think, what we just saw. Yeah, that's the same thing. You can also subtract away integrals. And additivity, if you have the same function f of x, you can take the integral from a to b. You can also consider an integral from that point b onwards to c, and it's equivalent to going from a all the way to c in one step. So you can break it up into segments. This is actually somewhat useful in a case where you might need to deal with a hazard at point B, such as a discontinuity at B. You might need to avoid that. This could be useful for avoiding discontinuities. And we have the max and min inequality. If f has a maximum value and a minimum value on a to b, you have this minimum of f is multiplied by b minus a, the width of it. And it means that, and then you have this max of f, the highest point on this f function divided by the width of the integral b minus a. So it means that that integral must be between these two values, that it must not be any larger than the maximum point, and it must not be any smaller than this minimum point. Basically the area of the minimum area and the maximum area. These are both crude rectangles that can be drawn on the curve, and with these are basically the boundaries of the integral. And so this integral must be in between these two. This rule you probably won't use too much. And the last one, domination, is similar to the previous one. If f of x is greater than g of x from this interval a through b, these two integrals from the same region, f of x will always be larger than g of x, or it could be equal to, if in cases where f of x is equal to g of x. Then there could also be an inequality over here too. And if f of x is greater than 0 on this interval, the integral would also be greater than 0. And so those are some of our rules that we can use to simplify. And so here is an example. This is a transcendental function. You haven't seen too many of these, but most likely. But evaluate this integral. I have to warn you, there's a little bit of a trick. So pause this video and make a try at it. Okay, so I hope you didn't spend too much time on this integral, because this is sort of a trick problem. This integral right here is actually a function that is really, really difficult to solve. But it doesn't matter, because look at these boundaries from 5 to 5. It's 0 width. There's no width of this integral that's going to make it equal to 0. So you didn't really have to do any analysis of that function at all. And so the integral is 0. Even though this was a really wicked transcendental integral, this integral was actually used quite a bit in statistics, and is most directly solved using numerical methods such as Riemann sums. If you actually do write the integral to this, send me an email. I'd love to see it. Here's another example. The integral from 0 to 3 of negative 12x cubed minus 9x squared minus 4x. This is just like the going backwards on a power rule derivative. Pause this and take a try at it. Okay, so let's take a look at our solution. First thing we can do is we can break this up into three simpler integrals. The negative 12x cubed, the 9x squared, and the negative 4x. And yeah, you can even take this negative outside. You can even take the negative 4 outside. Take this negative 12 outside. That's our constant multiple rule, and you end up with a formula that looks like this. So yet even more simplified now. And we have x cubed, the integral, we have an x squared integral, and we just have the x integral. This really is starting to resemble the antiderivatives from the previous chapter. And so using the power rule, the integral of x to the n dx is equal to x to the n plus 1 over n plus 1. That's true for any case except for when n is equal to negative 1. And when n is equal to negative 1, you get a division by 0. So there's a special case that you'll see in several classes later that deal with a case of in which n is equal to a negative 1. And so by doing this power rule, we get x to the 4th over 4, x to the 3rd over 3, x squared over 2. Those are valid integrals. And now we're dealing with a subset of this integral from 0 to 3, so we apply these ranges to it. I did do a little bit of simplification. Negative 12 divided by 4 is a negative 3. 9 divided by 3 is 3, and you got a negative 2 here. And so when we do these definite integrals, you basically substitute in for x's for each of these. You put in 3 for the x to the 4th, and you get 3 to the 4th times 3, negative 3. But you also do the 0 term too, minus 0 to the 4th. And so you end up with negative 3 times this difference. That you have negative 3 times 3 cubed minus 3 times 0 cubed. You have negative 2 times 3 squared minus negative 2 times 0 squared. And this ends up to being 3 different numbers that are added up, and you get negative 180. And it's sort of odd. We got a negative number. We got a negative area. You know, so what does that tell you about the graph of negative 12x cubed minus 9x squared minus 4x from this region of 0 to 3? It tells you that the graph is beneath the x-axis. It's negative there. And so we have our graph. This curve, I don't know its specific shape, but it's probably something like this underneath here, and this area, negative 180. This, or if you're looking at it from the perspective of being on a negative x, the area that I shaded is 180. But it's below the x-axis, so it's negative 180. And so you have this one integral. This is a case where f depends on x and y. And from 0 to 3 of 4y x squared. Try this one out. See if you get the same answer. And so pause it and come back to me. Okay, well, first thing I see here is the 4 can come outside the integral. That's for certain. 4 is a constant multiple. And well, and guess what? So does y. Yeah, we assume that y does not depend on x, that y is not a function in itself that has any x terms in it. That if that is true, then this entire 4y is not going to affect the curve as x changes, and so it comes outside. And it reduces this to just the integral from 0 to 3 of x squared. And the reason why y comes outside is because this is a dx. It's not a dy. So we're only concerned with what x's are doing. No, all other variables in there, if they don't change as x changes, we're not interested in them. And they can be treated as like constants and come outside that integral. That's a simplification to turn a mean-looking integral into something a little bit more friendly, like x squared, which is a power rule integral. So I guess I didn't solve this one to its completion. So x squared, the integral of x squared is 3 over 3, and it's going to be evaluated from 0 to 3. And this is all going to be times 4y, for whatever y is equal to. So we're going to have 3 cubed. That's going to be 27 over 3, which is going to be equal to 9. So you have 9 times 4y, you have 36y. So that's as simplified as we can get it until we find out what y is equal to. So the area under a graph of a non-negative function. It's another section of this chapter. We have, so basically the area between a curve and our axis y equals 0, that's our x-axis. You have the region of this that's a definite integral. If the graph of this function ever falls below this line, it starts subtracting from this total area. So if you want to find the total deviation from the y-axis, you will want to break up the integral into the regions and sum these regions' absolute values individually. So that's because when the line goes beneath y equals 0, it turns negative, and you get a negative area. So if you have a graph, let's say, and it waves around here, and then it goes here, and maybe up again, and then on upwards to infinity and beyond. And so you have one area here that's positive. You have this area that's positive, but you've got this area that is negative and subtracting away from the negative area before you start going positive again. And so you're going to have a definite integral, let's say, that goes from let's say right here, whoops, from right here to maybe, let's say, out here. You would need to additionally break up the integral at these points where it crosses 0 and do them individually. So you'd have one integral, you'd have another, you'd have another, you'd have another. We have, oh yeah, there's another place where it crosses 0. And so you need to break this up into 5 integrals and solve them individually. And keep in mind that these are going to be negative, so you need to change the sign to those to make them positive. And then you would have the area of the total deviation from our y-axis. Well, it's not our x-axis, y equals 0. So if you need to consider that total area, this is what you would have to do. So yeah, the average area value of continuous functions. If f is continuous, you can find the average value of it from between 2 points A and B with this formula. Notice that it's 1 divided by B minus A. So that actually is like, think of this as like the width of a rectangle that's bounded between point A and point B. Then you have this, so that's in the denominator. And in the numerator, you have this area. That's the area under the curve. I think it's a little bit better to draw this as an integral like this over B minus A. And I've got to draw the A and the B up here because this is a definite integral. So you have the area divided by the width, and what you end up with is the average elevation. I'll just call this E bar, average elevation of your curve. Basically, you're taking this curve and we're representing it as an equivalent rectangle with exactly the same amount of area and the exact same width. So you can find the average of a function within a certain area, within a certain range, by using this rule. And so that's our last slide. So that concludes this for chapter 5.3. So have fun with it. I hope I helped you out with it.